Imagine telling a motor to move to a position and it actually checks if it got there. That is what a servo motor does. In this lesson, you'll learn how a servo motor knows where it is, how Arduino communicates with it, and how to control its position with precision in a real project. This is lesson 19 of the 24-part series called Arduino for Beginners. Servo motors first became popular in radio control systems like cars, airplanes, and boats. They were designed to move mechanisms to exact positions, steering angles, control surface, and camera mounts. Because of that precision, they became essential components in robotics and Arduino projects. A servo motor is not just a motor, it's a complete positioning system inside a small enclosure. 5 main parts work together: a DC motor, a gearbox, a servo horn, a potentiometer, and an internal control circuit. The DC motor provides rotation. Like any DC motor, it spins when voltage is applied, but on its own, it spins too fast and with too little torque for precise positioning. That is why the motor connects to a gearbox. The gearbox reduces speed and increases torque. This allows the output shaft to move with control and enough strength to drive external mechanisms. Attached to the output shaft is the servo horn. This is the part you connect any mechanical system. When the shaft rotates, the horn moves with it. Now comes the key to precision: feedback. Inside the servo, the output shaft is mechanically linked to a potentiometer. As the shaft rotates, the potentiometer rotates too. Because a potentiometer changes voltage based on its position, it provides a continuous electrical signal representing the current angle of the shaft. This signal goes to the internal control circuit. The control circuit constantly compares two values: the desired position sent by the microcontroller and the actual position measured by the potentiometer. If those values are different, the circuit powers the DC motor in the direction that reduces the error. When both values match, the motor stops. This continuous comparison is called closed-loop control. The servo is always checking where it is and correcting itself. That is why it can hold a specific position even if external forces try to move it. Now the most important question: how does Arduino tell the servo which position to reach? The communication happens through timed pulses, commonly called PWM signals. However, for hobby servos, the important factor is not the average power of the signal. What matters is the duration of each pulse. A servo expects a pulse roughly every 20 milliseconds. Inside that repeating signal, the length of the high pulse encodes the target position. A pulse around 1 millisecond corresponds to one end of the rotation angle. A pulse around 1.5 milliseconds corresponds to the center position. A pulse around 2 milliseconds corresponds to the position end. The servo's internal circuit measures the pulse width and then moves the motor until the feedback potentiometer confirms the shaft reached that position. So, Arduino does not directly control motor speed or power. It simply sends position instructions encoded in time. The servo handles the control logic internally. Different servos may support different angle ranges or pulse timing, so checking the datasheet is always recommended. In this lesson, we use the SG90 micro servo. It typically rotates about 100 degrees and is widely used in beginner Arduino projects. It has 3 wires: power, ground, and signal. The signal wire connects to a digital pin capable of generating timed pulses. That is enough theory for now. Let's make the servo move in a cool project. Before continuing, a quick thank you to DFRobot for sponsoring this video. DFRobot provides a wide range of open source hardware for makers, students, and educators. For this series, they provided the Mind Plus Arduino coding kit, which includes sensors, actuators, and accessories designed specifically for learning. If you want to follow along with the lessons using the same components I'm using, you can find the kit through the link in the description. Thank you again to DFRobot for sponsoring this series, and and helping make STEAM education more accessible for everyone. In today's project, we will control the position of a servo motor using a rotation sensor and display the current angle on an LCD screen. For this project, you need Arduino Uno, input-output expansion shield, rotation sensor, servo motor, I2C LCD screen, and jumper wires. Start by attaching the expansion shield to the Arduino board. Connect the servo motor to digital port 3. Connect the rotation sensor to analog port A3. Connect the LCD module this way: LCL to A5, SGA to A4, VCC to power, and GND to ground. That completes the hardware setup. Next, open the GitHub repository for the series and download the sketch for lesson 19. Before uploading, install the required LCD library. When it's ready, upload the code. When the system starts, the LCD displays the servo angle. As you rotate the knob on the sensor, the servo moves smoothly to the corresponding position. Small rotations produce small movements. Large rotations move the servo across its full range. You are not just spinning a motor, you are commanding positions. This simple setup demonstrates the fundamental idea behind many robotic systems, translating user input into controlled motion. Now let's understand how the code makes this happen. At the beginning of the sketch, we include the libraries needed to control the servo and the LCD display. Then we define the pins and create objects representing each device. In the setup function, we initialize the servo and start communication with the LCD screen. This prepares both devices to receive commands. The core logic lies inside the loop function. First, the Arduino reads the analog value from the rotation sensor. This value ranges from 0 to 1023 and represents the physical position of the knob. Next, we convert that sensor reading into an angle between 0 and 180 degrees. This conversion is important because the servo expects a target position expressed as an angle. After calculating the angle, the program sends that value to the servo. Internally, the Arduino library generates the timed pulses required to represent that angle. The servo receives those pulses and moves until its internal feedback system confirms the target's position. Finally, the program updates the LCD to display the current angle. This gives us real-time feedback about the command being sent to the servo. So the full chain is simple but powerful. User input, electrical signal, position, command, control motion, visual feedback. The same control principle appears everywhere in robotics. And that brings us to something exciting. Precise control of motion is one of the core building blocks of robotics. The same feedback principles used inside this small servo are also used to stabilize robots, control mechanical arms, and even manage flight systems. That is why I've been working on a new masterclass about building drones with Arduino. In that course, we'll explore how sensors, control algorithms, and actuators work together to maintain stability, manage power, and control movement in three-dimensional space. If you want to learn how these concepts scale from a simple servo to a flying system, you can join the waiting list using the link in the description below. Then you'll be the first to know when this masterclass is available. That's it for today's lesson. Now you understand what a servo motor is, how it achieves precise positioning, and how Arduino communicates with it using timed pulses. If you enjoyed this lesson, subscribe so you don't miss the next ones in the series. And before you go, check out the video appearing on your screen right now. It will help you continue building your Arduino skills step by step. Thanks for watching to the end, and I'll see you in the next lesson.